Hello, welcome. In the previous part of this lecture, we discussed basis and dimension of a vector space. And we showed how to calculate the dimension of subspaces. In this part, we're going to talk about row space and column space of a matrix and rank of a matrix. Let's begin the discussion with the notion of row and column vectors of a matrix. Let A be an m by n matrix over the set of real numbers. Consider a vector with components a sub 1 1, a sub 1 2, and all the way up to a sub 1 n. This vector is called a row vector corresponding to the matrix A. Similarly, a vector with components a sub 2 1, a sub 2 2, all the way up to a sub 2n is another row vector corresponding to the matrix A. We can denote these row vectors as similarly, if we can consider a column vector with components a sub 1 1, a sub 2 1, all the way up to a sub m1, then this would be called a column vector corresponding to the matrix A. The column vectors corresponding to the matrix A may be denoted by definition. The vectors r sub 1, r sub 2, all the way up to r sub m, with components as shown, are called the row vectors of the matrix A. Similarly, the vectors c sub 1, c sub 2, all the way up to c sub n, with components are called the column vectors of the matrix A. We note that each row vector is an element of the vector space Rn. And each column vector is an element of the vector space Rm. Since the matrix is of order m by n, so each row vector has n components and each column vector has m components. Definition. The row space of a matrix A is denoted by this symbol, is the subspace of Rn spanned by the row vectors of A. Similarly, the column space of the matrix A may be denoted by this symbol, is the subspace of the vector space Rm spanned by the column vectors of A. In other words, if R sub 1, R sub 2, all the way up to R sub m, and C sub 1, C sub 2, all the way up to C sub n, are the row and column vectors of a matrix A, respectively, then the row space of A is the span of all the row vectors of the matrix A. Similarly, the column space of A is the span of all the column vectors of the matrix A. In short, the row space of a matrix A is the space generated by all the row vectors of the matrix A. Similarly, for the column space, we observe that the column space of a matrix A is equal to the row space of the transpose of the matrix A. In other words, the column space of A is the same as the row space of the A transpose. Which is clear from this figure. We see that the row vector of the matrix A transpose is simply the column vector of the matrix A. Similarly, the column vectors of the matrix A transpose is same as the row vectors of the matrix A. Recall that two matrices are called row equivalent if and only if one can be obtained from another by a sequence of elementary row operations. For example, the matrices A and B are row equivalent since the matrix B can be obtained from the matrix A by applying some elementary row operations. Theorem: if a matrix A is row equivalent to a matrix B, then the row space of A is equal to the row space of B. Please see the proof in the appendix. In this example, we want to show how to find a basis and dimension of a row space of a given matrix. Let's have a look at the solution of this problem. We can reduce the matrix A by applying a sequence of elementary row operations to its row echelon form to obtain the matrix B. We observe here the matrix B is the row echelon form of the matrix A. It's not necessarily the reduced row echelon form of the matrix A. The non-zero row vectors of B in row echelon form are these three rows. Let's denote them by W1, W2, and W3. Hence, the set S of the non-zero row vectors of the matrix B forms a basis of the row space of B. Thus, by the theorem 11.2.1, the set S is a basis for the row space of A. And the dimension of the row space of A is 3. Since the set S contains 3 elements. In the next example, we want to find a basis and calculate the dimension of the column space of the same matrix A, as in example 11.2.1. Since the column space of A is same as the row space of A transpose, by reducing the transpose of A to its row echelon form, we obtain the matrix B, whose pivots are which correspond to the non-zero rows of the matrix B. Therefore, the non-zero row vectors of B in row echelon form are W1 with components 1, 0, -3, 3, 2, and W2 with components 0, 1, 9, -5, -6, and 0, 0, 8, -8, -4, which is W3. Hence, the set S of the non-zero row vectors of the matrix B forms a basis of the row space of B. Thus, by the theorem 11.2.1, S is a basis for the row space of A transpose. Since the row space of A transpose is exactly same as the row space of its row echelon form, namely the matrix B. This is equivalent to saying that the set S prime of vectors v sub 1, v sub 2, and v sub 3 forms a basis for the column space of the matrix A, since the column space of the matrix A is same as the row space of its transpose. where v sub 1 is the transpose of the vector w1, hence a column vector with the same components as the vector w1 but written in a column form. Similarly, the vectors v sub 2 and v sub 3 are transposes of the row vectors w sub 2 and w sub 3 respectively. The dimension of the column space of A is 3. Since the basis for the column space of A, namely the set S, has 3 elements. Definition: the dimension of row space of a matrix A is called the row rank of A, and the dimension of the column space of a matrix A is called the column rank of the matrix A. The next theorem tells us that for a given matrix A, the row rank is same as the column rank. For any m by n matrix A, the dimension of the row space of A is exactly equal to the dimension of the column space of A. In other words, the row rank of a matrix is equal to its column rank. To see the proof of this theorem, please consult your textbook. Since by the theorem 11.2.2, the row rank of a matrix is same as its column rank, now we can define the rank of a matrix as in the definition 11.2.4. The dimension of the row or column space of a matrix is called the rank. And it is denoted by the symbol rank of a matrix A. Let's see an example. Find the rank of the matrix A. From the examples 11.2.1 and 11.2.2, we find that the dimension of the row space of A is exactly same as the dimension of the column space of A, which is equal to 3. Hence, the rank of the matrix A is equal to 3. With this, we end the part 2 of this lecture. In the next lecture, we're going to talk about coordinates of vectors in a vector space. And how do these coordinates change under the change of basis? Thank you.